if the sine of 30 degrees is equal to 1/2, that means the inverse sine of 1/2 equals 30 degrees. We're always taking trig functions of angles to get ratios. And we're always taking inverse trig functions of ratios in order to solve for angles. So whenever you're taking an inverse trig function, you're coming up with an angle as an answer. Now, whether it's in degrees or radians does not matter. In other words, I can write it like this also. And it's still, you're taking trig functions of angles to come up with ratios. Now, because if you know what an inverse is, an inverse function is if you take a function and take its reflection across that green line. That green line is y equal x. Okay? In other words, that's how you get inverses, is by reflecting a function over that green line. However, if I took the entire sine curve, in other words, my red and the black part, and reflected it over that green line, I would end up with a vertical squiggly line, which would not be a function because it would not pass the vertical line test. You with me? Okay. So what mathematicians have done in order to avoid that is they restrict the domain of the sine function from minus pi over 2 to pi over 2. And that's the fourth quarter and the fourth quadrant and the first quadrant. So in other words, they only deal with what I have in black there. Okay? Now, if I were to reflect that, I'm not sure I drew it quite right, but it's going to look something like that, right? Still with me?
Yep.
And whenever you take the inverse of a function by reflecting it over the line y equal x, then you also switch domains and ranges. So my new domain for my red line is, this is pi over 2. This is minus pi over 2. This is 1. And this is minus 1. So if I erase everything except my red stuff, we erase the green line. We don't really need it, as long as you understand that's how all inverses work. In other words, now the red line is a function. It passes the vertical line test. Okay? So if I said to you, and I can label that red line as y equals inverse sine of x. So what is the inverse sine of 1? According to my red line. My red... I
don't know.
Well, plug in 1 for x, and where is it on the y-axis?
1.
No. Oh, read the red grid. Remember, we had to switch the domain and range. So the x-axis is no longer the one that's in pi, radians. It's now the y-axis that is. So let me erase everything that I should have erased. That 1, that pi over 2 and that pi over 2. So if you go to the x-axis where the point is 1, right there, what's the y-coordinate of that?
Coordinate, pi squared.
No? What's this coordinate right here? It's my y-coordinate. The x-coordinate's 1. Read it off the y-axis.
1 pi squared.
Pi over 2. Perhaps you were reading that as pi squared. That's pi over 2. Okay? Which is 90 degrees. So the sine of 1, the inverse sine of 1 is pi over 2. What's the inverse sine of negative 1?
The inverse sine of negative 1.
Uh-huh.
Negative pi over 2.
Correct. All right. Now that you understand that, it's important. In other words, this is what mathematicians have come up with by convention, to restrict the domain from minus pi over 2 to pi over 2. And what that means is that when you take inverse sines of certain angles, you get either pi over 4. In other words, we're taking the inverse sine of a number, a ratio, to get pi over 4. And if we take the inverse sine of a negative number, our answer in our calculator is always going to be a negative angle. So inverse sines of positive arguments give you first quadrant angles. This area here is first quadrant. And of negative arguments give you not the third quadrant, but the fourth quadrant, which is a negative angle. And that's what your calculator is going to do also for inverse sines and inverse tangents. Sine and tangents, two dominant quadrants are first and fourth. In other words, if you take the inverse tangent of a number, you'll get, if it's a positive number, you'll get the first quadrant angle. If it's a negative number, you'll get the minus angle, which is in the fourth quadrant. Cosine is split up different. Cosine, they didn't restrict the domain from minus pi over 2 to pi over 2. They restricted it from 0 to pi. So when you talk about inverse cosine, you're talking first and second quadrants. Your calculator will never give you a third or a fourth quadrant answer for inverse cosine. All right, let's have a look at your documents here. Hold on, just a second. Using a graphing utility to complete the table. And this is the function y equals arcsine of x. Well, use a graphing utility. So I presume they want, okay, well let me pull up my graphing utility and we'll graph that, and then you can read off the graph what the answers are going to be for this table. I'm sure you know how to do this on your calculators. All I'm going to put in there is y equals arc sine of x. And we'll have a look at what they've got here. Notice that they drew it just like I was talking about. And that point on the y-axis, that's minus pi over 2. Notice that minus 1.5 and change is minus pi over 2. This point on the y-axis is pi over 2. Okay? So to complete this table, when x is minus 1, what is a decimal value? You're going to have to probably write these down. I presume you have to turn these in. This is homework?
Yeah.
Okay. Why don't you go ahead and fill in the table as we go through each of these.
All right, let me get some.
What's the inverse sine of minus 1? Now, assuming that they want you to read the graph, then let's give them answers that are in decimal, since that's what my graph shows, is the decimal answers. In other words, my graph doesn't show pi over 2 and minus pi over 2 like you would prefer. And if you put it into your calculator, you'll probably get pi over 2 or minus pi over 2. I'm not sure. But as long as we're reading off of this graph, let's use decimal answers. So what's the sine of the inverse sine of minus 1?
Inverse sine of minus 1.
Mm-hmm. That blue graph is the inverse sine.
I'd probably say negative pi over 2.
Okay, you can put that down, but I would say put down minus 1.57. Notice that that's a reasonable approximation to pi. The only reason I'm saying that is because they're giving you decimal answers here. These are not standard answers to common angles. Okay, so what is the inverse sine of, according to this graph, negative 0.8? I've got it on negative 8.8 right now.
1. Negative 1.
I would say negative 0.9. Notice where it crosses the y-axis is above the minus 1.
Mm-hmm.
Okay. Now, are you writing these down?
Yeah, I was getting paper, but...
Go ahead and get some paper, because if you're going to have to turn these in, there's no point in you doing all of this work over again. You might as well be writing down the answers as we're doing it.
Okay, 1 sec.
Okay? Okay, you back? Jake?
Yeah, I'm back.
Okay, do you have your calculator in front of you by chance?
I don't have a graphing calculator right now.
Okay. Well, then let's use my calculator. The best way to do it would be to, if you graphed it and you completed the table based on your graph. But we can go through it. It's just every 0.2. So for negative 0.8, the answer is minus 0.9. And what is it for negative, hold on, there, that looks like negative 0.6, as close as I can get to it. Hold on, 1, 2, 3, 4, 5, 6, yeah. So what's the inverse sine of negative 0.6?
Wait, what? Sorry, spacing out.
What's the inverse sine of negative 0.6? That's where I have my cursor on that graph.
About negative 0.6.
Okay. Now we'll go to negative 0.4. Hold on, let me get it on there. Let's see. Boy, they don't make these tick marks very big. Here, let me blow this up. Yeah, that's better. 1, 2, 3, 4. So here's 4. Okay, hold on. What's that inverse of negative 0.4?
About negative 0.3.
Okay. Not quite sure why they're wanting you to do all of this, but we'll do it. Now I'm at negative 0.2.
About negative 0.1. Negative 1.5.
I would call it negative 0.2. In other words, read the hash marks. I don't know if you can see them very well, but that's about at the second hash mark going down. So that's negative 0.2.
Mm-hmm.
Okay, and then we're going up by tenths. What's the inverse sine of 0?
0.
Okay, how about the inverse sine of 0.2?
0.2.
Notice that these are all going to, the positives are going to be the same as the negatives, only with a positive sign. So whatever you wrote down for minus 0.8, minus 0.6, minus 0.4, minus 0.2, write down the same number for 0.2, 0.4, 0.6, 0.8, and then what's the inverse sine of 1?
0.9.
No, the inverse sine of 1. There's 1.
Oh, pi over 2 at 1.57.
Good. Okay. So that completes those first two tables. You with me?
It.
Okay. Plot the points from the table in part A and graph the function manually. Okay, well we did that. Use the graphing utility to graph the inverse sine and compare the result with your hand-drawn graph. Okay, we'll assume we did that. That's what my first 5 minutes was all about. Determine any intercepts and symmetry of the graph. What kind of symmetry are you looking at here?
I don't know.
That is symmetry about the origin. Sine is an odd function. Odd functions have symmetry about the origin. And what that basically means is it's a reflection over the y-axis followed by a reflection over the x-axis. And if you look at that curve that we're looking at, it has symmetry about the origin, as does the sine function. In other words, if we go back and we look at my graph, notice the black also has symmetry about the origin. Cosine does not. Cosine has symmetry about the y-axis only. And cosine is an even function. And even functions all have the property, let's go over this as long as we're talking about it. An odd function means that the sine of negative x is equal to the negative sine of x. That's odd. Even functions, like cosine, mean that the cosine of negative x is equal to the cosine of x. In other words, you can ignore the negative sign when you're taking the cosine of negative angles. But when you're taking the sine of negative angles, you can't. Just turn it into negative the sine of a positive angle is the easiest way to deal with it. Determine any intercepts. Well, what is our intercept of that blue line? What's the x-intercept?
I don't know.
What's the intercept mean?
Where they cross.
Well, where's it cross the x-axis?
Origin.
Okay. What's the y-intercept?
To origin.
Correct. Okay. So we figured out all intercepts and symmetry. Now, number 2 wants you to do exactly the same thing, only with inverse cosine. So let me get it up here. Very interesting. Yeah. Notice that the inverse cosine goes, its range of the domain restricted inverse cosine goes from 0 to pi, right? In other words, this point right there on the y-axis is pi, 3.14. And what is the cosine? Okay, so let's go through these again. Starting at -1. What is the inverse cosine of -1?
3.
3.14. We know it's pi. Boy, they sure don't make these points very... It's awful hard to read. I'll try to get on point 8. All right. Gosh. What's the inverse cosine of -0.8?
2.4.
2.5, I would say, maybe. All right. And let's see, 6 has to be this one right here. It's the inverse cosine of -0.6. I don't know what happened to the horizontal line. There it is.
2.2.
Okay. How about -0.1234 is right here. Okay. -0.4.
2.0.
Okay. -0.2.
-0.2. About 1.9, 1.8.
1.8, I would think. And finally, 2 hash marks. Where is the second hash mark? God, I can't hardly tell. We'll call it there. That's pretty close. So negative 0.2. It's what?
What?
Negative 0.2, the inverse cosine of that.
1.8.
Okay. 0.
1.6.
Okay, what do we know that has to be also in terms of pi? Slightly above 1.5.
Pi over 2.
Right, so that's got to be 1.57. And now the positives are not the same as the negatives with a different sign on them, like sine was. Okay? Notice the positives, we're going to keep going down. So what's the inverse cosine of 0.2?
1.4.
Okay, and 0.4?
1.2.
And 0.6.
About 1. 1.1.
And 0.8.
0.8.
I would say 0.7 maybe.
Yeah.
Okay.
Opposite.
And finally, 1.
Just 0.
Okay. And that makes sense. The inverse cosine of 1 is 0. Why? Because the cosine of 0 degrees is 1. All right. So we've got that. Now let's answer some of their questions. Determine intercepts and symmetry. Does this thing have any symmetry?
No.
The only kinds of symmetry you need to look for are either symmetry about the x-axis, symmetry about the y-axis, or symmetry about the origin. Does this have any of those? Which one?
Across. I don't think there is one.
No, there isn't. In other words, if I reflect it, the part that's to the right of the y-axis over the y-axis, I don't get the part on the left. And if I reflect the whole thing over the x-axis, I don't get any part of it either. So this has no symmetry on the inverse function, but just out of curiosity, it does have symmetry on the function itself. In other words, if I draw the cosine curve, looks like that, but if I keep drawing it on both sides, notice that it has perfect symmetry with the y-axis. And also, if we start taking angles, like we'll call that pi over 6, if I take the cosine of pi over 6, I get that point right there. Well, if I take the cosine of negative pi over 6, I get the same value, same y value. So my cosines of positive first quadrant angles are exactly the same as my cosines of negative, which are fourth quadrant angles. And notice that if I were to restrict the domains between there and then try to find the inverse, it would not pass the vertical line test. So I can't restrict with cosine the domain from minus pi over 2 to pi over 2. So they've restricted it from 0 to pi. In other words, this part of it right here, which is the first and second quadrants. So when I flip this thing about that y equal x line, I get the curve that we're looking at in Wolfram alpha. Hold on, sorry. All right, let's see. How about intercepts? Is there an x-intercept?
Yes.
Where?
1.
1 comma 0, okay. And there's a y-intercept where?
Pi over 2, or 1.57.
Good. All right, so we're down to problem number 3. And they want you to do the same thing for arctan, the same exact thing. Well, if we do that, we're going to use our entire hour up doing these first 3 problems.
I don't think that's entirely necessary. So.
No, I don't either. Plus, you should do one of these on your own calculator. In other words, doing it the way we've done it is fine for you understanding it, but for you to actually do this exercise, they want you to do it on your own graphing utility. It doesn't have to be your calculator. You could go to Wolfram Alpha and do it on your own. Exactly what I've done. You should probably have Wolfram Alpha on your computer just so that when you forget your calculator, you'll have something that we can look at.
Oh, I downloaded it called Desmos on my iPad.
Oh, okay. So you have something like that. All right.
Yeah.
But for now, let's go on. Yeah. And notice what they're saying is the same way I started out the session. If the sine of an angle equals 1, then the inverse sine of 1 equals that angle. Whether that angle is in radians or degrees does not matter. Okay? So what's the sine? If the sine of pi over 6 equals 1/2, what's that mean in blue?
Sorry?
Number 4.
Oh, I would say it's not,
Look at their example.
the inverse of sine, or arcsine, would be arcsine of 1/2 equals pi over 6.
Good. And number 5.
Arctan of -1 equals negative pi over 4.
And 6.
Cosine of pi over 4 equals 2, square root of 2 over 2.
Good. And 7.
Sine of negative pi over 2 equals -1.
Okay, good. And 8 through 15, it says evaluate using a calculator. Well, yeah, you'd put it in exactly as I would put this in here. In fact, let me do 1 or 2 of them on Wolfram Alpha. And I'm going to do it exactly what I'm looking at. Sine of 1/2. Excuse me, the arc sine of 1/2. Let's see if I needed parentheses there. Nope, it put them in there for me. And it gave me the exact result. And notice that it gave me the result in radians. How nice. That's what we want. We didn't want an exact number. That happens to be 0.5235, but now we're talking in radians. Okay, so that's all you have to do is put all these into your calculator. And they're all inverse. So what kind of calculator do you typically use?
I typically use...
Is it an Inspire or a TI-84?
TI-84 usually.
Okay, that is the second key. In other words, it's the blue key above the sine is the inverse sine. Of course, arc sine and inverse sine mean the same thing, as Wolfram Alpha shows here. Okay, well, let me close this out, open up the second document, and we'll start with 15 or 16. Let me see if there's any ones that are interesting even in that. No, that's just a question of using the proper key and putting in the argument. And on your calculator, you may need these parentheses. I'm not sure. If you have ratios, I would say yes. I was kind of surprised that Wolfram Alpha didn't need them. Notice I didn't put the parentheses.
Yeah, I did.
It could have maybe interpreted that as the arcsine of 1 all divided by 2. But if you put parentheses, then it's crystal clear, and it assumed I meant parentheses. All right, so let's look at 16. Blow it up a little bit so you can see it. Determining the missing coordinates on the points on the graph of the function. The function on the left is the inverse tangent of x. Okay, so let's look at this point right there. What is the x coordinate that gives you pi over 4 as an answer? What's the tangent of pi over 4? 45 degrees.
I don't know. Tangent.
Picture the 45-45 right triangle and figure out what the tangent of 45 is.
1/1.
Okay. So what's the missing number in this point on the right here?
1/1.
Correct. That's pretty easy. We just could read it right off the x-axis. So that's 1. That's 0. What's this point here have to be such that the tangent of that number is equal to minus pi over 6? What angle is pi over 6?
I don't know.
Let me give you a really easy way to memorize. In fact, this is probably the best way to convert from radians to degrees. Pi over 6 is equal to 30 degrees. Notice 30 times 6 is 180. Pi over 4 is equal to 45 degrees. Notice 4 times 45 is 180. Pi over 3 is equal to 60 degrees. You get the picture? What's 2 pi over 3 equal to?
120.
Yeah, in other words, 2 pi over 3 is 2 of these. So we just multiply 60 by 2. What's 3 pi over 4 equal to?
135 degrees.
Yeah, now I don't know about you, but to me, this is an easier way to convert radians to degrees than the typical method that they usually want you to use, which is to multiply by 180 over pi. But notice 7 pi over 6 has to be 7 of these 30-degree angles, so that's got to be 210. So the simple ones, the ones on the left where pi is the numerator, are super easy to convert. These two numbers have to multiply to 180. And the harder ones, these, well, if you start with the ones on the left, they're pretty simple to convert to degrees also. See that? All right. So, hold on a minute. Let me pull up my picture again. I'm going to put both triangles on here because this is the starting spot for all trig. If you do not remember these two triangles, try to memorize their dimensions because this answers an awful lot of questions. What's this side equal to?
Which one?
One opposite the 30?
1.
What's the one opposite the 60?
2.
Oh, that's square root of 3. And that's 2. And on the 45, 45, right triangle.
1, 1, and square root of 2.
Yeah. Okay, so in this problem, they're saying, what's the inverse tangent of negative 30 degrees? Well, what's the inverse tangent of 30 degrees? What's the tangent, excuse me, what's the tangent of 30 degrees equal to?
1 over square root of 3, or it's just 3, square root of 3.
You know what? It's 1 over square root of 3. Now, I had a student the other day that said his trig teacher told him not to rationalize these. With trig, you're better off not rationalizing it. And it's okay to give an answer 1 over square root of 3. If we had to rationalize that, that would have to be square root of 3 over 3. Hold on, I wrote it wrong. Tangent of 30 degrees equals 1 over square root of 3. So therefore, the inverse tangent of something has to equal pi over 6. So that something would be what? If it was positive. In other words, this is 30 degrees. So if the tangent of 30 degrees is 1 over square root of 3, then the inverse tangent of what equals 30 degrees?
1 over square root of 3.
Yeah, so if we look back at that problem, and we look at this point right there, their answer is negative 1 over square root of 3. For the x-coordinate. And notice that that number, negative 1 over square root of 3, is a number less than 1, right? 1 divided by 1.7 approximately. And sure enough, on the x-axis, it is less than 1. So negative 1 over square root of 3. You see why that is that point right there? Okay. Now let's look at that third point on the far left. Here we're missing the y-coordinate. So they want the inverse tangent of square root of 3. Well, if I pull up my graph that I just had, what's the inverse tangent of square root of 3? Looking at this graph, or that triangle.
1 over, I don't know.
Well, square root of 3 is square root of 3 over 1, right? So the tangent of what angle equals square root of 3 over 1 by looking at the triangle?
Negative 30.
No, 60. The tangent of 60 degrees is what?
Oh, okay.
Opposite over adjacent. So it's square root of 3 over 1. So what would go into this would be 60 degrees, which means the inverse tan of square root of 3 has to be 60 degrees. But they're talking the inverse tan of negative square root of 3, so that has to be negative 60 degrees, which in radians is how much? 60 degrees is how many radians?
Approximately.
No, not approximately. Pi over 3. Remember that pi over 3 is equal to 60 degrees because 3 times 60 is 180. So minus pi over 3 is what goes right there in that pink square. All right, let's go to arc cosine. Let's go to 17. This time let's go from left to right. I should have gone from left to right last time. This is arc cosine. For this one, let me draw the cosine curve. That's why when I first started the unit circle with you, I said you might as well memorize this curve because you're going to need it in lots of places. Now, this is the cosine curve, not the inverse. This is y equals cosine of x. Let me label a couple of these points. That's 1. That's -1. That's pi over 2. And that's pi. Okay. So if I leave that up there, so where is the cosine equal to -1? Looking at the far right, that curve right there.
About pi.
Okay, so on this inverse curve, the far left point where the x coordinate is -1, what is the y coordinate?
-1.
No. Let's go back again. Where is the cosine of what angle equal to -1?
Pi.
Okay. So where is the inverse cosine of -1 equal to?
1.
Pi.
Oh, yeah, because you
Notice
switch
why? In other words, right here is the point we're talking about. On the cosine curve, that point is -1. Excuse me. On the cosine curve, that point is pi, comma, -1. So on the inverse cosine curve, it's always just the reverse. You switch the domain and the range. So therefore, the inverse, the arc cosine of -1 has to be pi. So on the pink square on the far left, that's pi. Now, let's go to this one, the second dot there. This one, the reason I had to draw the cosine curve, because that was a quadrangle. Pi is a quadrangle, and you can't figure out quadrangles from these two triangles. I mean, you can, but I haven't taught you how to do it. Typically, to solve for quadrangles, you need the curve. However, if I go up and look at my triangles, I can solve for that point, because this is not going to be a quadrangle. What angle is the cosine equal to 1/2?
Sorry, what?
What angle, looking at the triangle, is the cosine of that angle equal to 1/2?
30.
No. Cosine of 30 is square root of 3 over 2. It's adjacent over hypotenuse.
That's 60.
Okay. So 60 degrees is the angle, but it's not 60. It's pi over what?
Pi over 3.
Positive or negative?
Positive.
Yeah, you can see that from the graph that it's got to be positive. And that's correct. Even the calculator would give you sorry, I'm wrong. Let me think for a minute. -1/2. Notice that that can't be 60 degrees, that angle that we're looking at there. And the reason is because it's -1/2, it has to be in the second quadrant. What's the equivalent of 60 degrees in the second quadrant?
I don't know.
120, the supplementary angle.
Oh, okay.
Okay, if you put into your calculator the cosine of 120 degrees, you'll get -1/2. If you put in the cosine, the inverse cosine of 1/2, you'll get 60 degrees. But if you put in the cosine, inverse cosine of -1/2, you get 120 degrees, which is 260 degrees, so it's 2 pi over 3. So that's what goes in that red spot right there, is 2 pi over 3. In the beginning, when you're working with trig and radians, it's okay to translate to degrees and then translate back to radians if you have to. Nobody expects you to be able to think in radians yet. At some point they will though, and it'll come natural. You should be able to kind of think in radians. And I could almost label this triangle as, label that angle as pi over 3 and this one as pi over 6. Okay. Okay, the third point on there. That is a pi over 6, which is what angle?
Pi over 6.
Mm-hmm.
At 30.
Okay, so they're saying the cosine of 30 is equal to what? From the what's the cosine of 30?
√3/2.
Okay, therefore the inverse cosine of √3/2 is 30. So what goes into that pink there is √3/2. And √3 divided by 2 is about 0.7, which is where they have it. All right. That's probably a good place to stop. We got through 17. What were you supposed to do through 23?
Yeah, but I could probably do that on my own.
Well, the rest of, 18 through 23 are just calculator problems.
Yeah, that's fairly simple, so that's...
Now, when it says round your answer to 2 decimal places, that means that they want you to use decimals, not pi over 2 or things like that. Although looking at all of these numbers, none of them are going to be, pi over 6, pi over 3, pi over 2. They're all going to be something else. And so just whatever you, make sure your calculator is in, you know what? You could be in radians or degrees. Doesn't matter. It's going to give you the right angle. The right number. In other words, the answer 18 through 23 are all going to be numbers. You're not going to, they're all going to be angles. When you take inverse trig functions, and every one of these is an inverse trig function, you take it of a number and you come up with an angle. Even if that angle is in radians, it's okay, but it doesn't specify whether it wants the answers in radians or degrees. So whatever your calculator is set on, it'll give it to you in that. And you maybe need to label your answer as either degrees or radians, but you don't have to have it set on either one. It'll read this argument as a number, and then it'll give you the answer in either radians or degrees, depending on what your calculator's set on. All right?
Good.
All right, Jake. Have a good one. I'll talk to you next time.
All right, thank you.